All right, thank you so much for coming today, and thanks Carl for organizing this special PUNLAG seminar. And I'm Yao Zhu from Department of Computer Science, and today I'm going to present a recent work on erasure coding for fault-oblivious linear system solvers. This is joint work with Professors David Glai and Anant Grama, and I would like to thank Professor Amit Same for his continuous support and guidance. And this project is funded by National Science Foundation and Army Research Office. So the problem we're looking at is linear system solvers, and we consider it in a distributed computing environment. And we look at this 8x8 matrix as a case to motivate our discussion. So in a distributed computing environment, one common approach to solve linear system is by slicing this matrix into row blocks and distribute them into processes. So we have 8 processes, and each one has one row allocated to it. And of course, each process will also store the corresponding component of the solution and the right-hand side. And the processes will, participate in an iterative method like conjugate gradient to solve this linear system. And for example, P4 needs to talk to P3 and P5 to acquire the intermediate values of x3 and x5 in order to complete its matrix vector multiplication. So now suppose at a moment, for some reason, for whatever reasons, P5 failed. It just died, crashed. And let's consider what does this imply for the whole distributed linear system solver. If that happens, P4 can no longer talk to P5. And because x5 is the component that is updated only at P5, there is no way to update x5 anymore if P5 crashes. Although P4 may cache some values, some intermediate values of x5 before the faults occur, but there's no way to continue the computation because the data of the rows stored on P5 is no longer available, and and x5 is no longer updatable. So more than one process may fail along the iterative method. P2, P8, they may all fail. So in conclusion, in a distributed linear system solver, we need some technique of fault tolerance so that the system can complete its job. So the available techniques, fault tolerant schemes we have, generally belong to these 3 kinds. The first is called checkpoint restart. The idea is that we periodically checkpoint the states of the system, like the intermediate solution, the search direction of the conjugate gradient. We write these intermediate states to secondary memory, like flash memory or hard disk. And then if one fault happens, we can go back to where we bookkept the intermediate value, and then we replay from there. However, this implies a huge I/O cost because you write to the secondary memory, which is much slower than the computation speed. And sometimes it's hard to identify what is the consistent checkpoint state that we can store or can bookkeep. The second kind is called active replicas. So the idea is that we just make several copies of each process. And if one copy fails, we have other copies to back up. But however, in general, if we have P processes and we want to tolerate K processes being failed, we need to make K plus 1 times P replicas. And usually, the fault occurs, at some rate. The rate is depending on the distributed system, and the K is proportional to P. So in total, this order is on P squared, and if you have more and more processes, the cost of replication just blows up. The third is called deterministic replay. A well-known example is called MapReduce. So the MapReduce consists of 2 stages: the mapping stage and the reduction stage. But this is very restricted in a computation model, which only applies to staged execution. And if there are many faults, the total job span, because each stage will be elongated. If many faults occur, the job span will be elongated a lot. So instead of being just fault tolerant, we ask the question, is there any way that we can be oblivious? We're not only tolerating the faults, we really don't care about the faults when they occur. So we want to see, is there a feasible way to do fault tolerant to fault oblivious? So we're going to describe, what is the benefits of fault oblivious. Of course, if we can, forget about the faults, just to behave as if no faults occurred, then we don't need to bookkeep anything. We don't need to roll back and replay. We don't need to stop the computation. We can just let the computation go on as usual, as if no faults happen. But still, we want to be able to recover the solution we want at the end. So we describe our approach based on erasure coding that facilitates this fault oblivious computation. So just as an overview of the erasure coding of the linear system, what it means that we have an input linear system. That's our target. We want to solve this in a distributed computing environment. And it's n by n matrix, and by assumption, here we assume it's SPD, and we call this linear system the raw system. Okay, just the input system. And that k be a parameter here. So k is the number, the maximum number of faults that our fault oblivious computation can tolerate or can be oblivious to. And then by somehow augmenting this raw system to something we call encoded system, that we can enlarge the matrix of A to be A tilde, which is n by k times n by k, n plus k times n plus k. And we will describe what's the relationship between the solution to this augmented system and the solution to the raw system. And the idea is that whenever faults occurred when we solve this encoded system, and we can forget about the code, the faults, and in the end we can still extract the solution to it, and then we can decode the solution to the raw system from the solution we acquired when we solve this encoded system obliviously, fault obliviously. So before we describe the encoding scheme in detail, let's take a look of the example. So here, the example, we assume that we tolerate one fault. Okay, it's 8 by 8 matrix. There is one process that can fail during the iterative method, and this is the input. This is the encoded matrix. So the intuition is that we compute the column sum of this matrix, which is 1 all the 0 until there's 1 in the end. And of course, because it's symmetric, the row sum will be the transpose of this column here. And we need to make it a square, so we have to put this number, which is equal to the sum of the row sum or the sum of all the elements in this matrix. So the column here, the row here, the element to put here, just we apply some coding to this matrix. Here we use the sum. Why? We add them up. So that the addition plays the role of encoding this matrix, introduce some redundancy here. Okay? So let's look at the process graph of this matrix. So we still have these 8 processes, but it's now 9 by 9 matrix. We have the newcomer, which is P9. Now P9 talks to both P1 and P8 because it depends on the first process and the last process for completing its matrix vector multiplication. So now still suppose a process fails. Okay, we claim that tolerate to one fault. Let's say P5 crashes. But now because we have P9 introduced, even P5 crashed, the other surviving processes, they can still talk to each other because they're still connected. Okay, just getting rid of this process does not disconnect the process graph. And in fact, we don't care which process failed. If there is only one process fail, it could be P2 or it could be P8. Okay, so only say requirement is that only one process fails, but no matter which one. So compare this with the active replicas. Active replicas, in order to tolerate one process fault, it needs to repeat everybody at least one more time. But here we just introduce one extra process, which is much better than active replicas. So in general, we claim that if we can encode this augmented matrix by k more columns and k more rows, we can be fault oblivious to k faults when we solve the encoded system. So now let's describe the encoding scheme. So we have the raw system, we have the encoded system, which is a 2 by 2 block matrix, where the 1, 1 block is this input matrix A, and then we introduce an encoding matrix, which is dimension n by k, because we are target at fault oblivious to k faults at most. And then we can encode the columns of A by A times E, and encode the rows of A by E transpose A. And we introduce the last 2, 2 block as a two-sided encoding of A. And now suppose we have that the actual solution to this raw system be x star, and we embed this solution to the n plus k space by padding all zeros at the end. And if we compute a tilde x star tilde, we'll find that the intended right-hand side for the encoded system will be equal to this form. And if we look at here, the encoded right-hand side only depends on the input right-hand side and the encoding matrix. So there's no knowledge of x star required, in fact. Okay, so we can achieve our encoding without any knowledge of what is the solution. Right? Otherwise, it's cyclic logically. So here are some properties which establishes that the encoding scheme we introduce will do what we want for the oblivious. So first, a tilde is SPS symmetric positive semi-definite with rank n if A is symmetric positive definite. And a null space basis of a tilde is E minus IK, and from this we can conclude that a very important property is that YZ be any solution to the encoded system, okay? Because the rank deficiency of a tilde, there are multiple solutions to the same right-hand side, but let's say YZ be any solution to this linear system. And we can prove that the padded components, the redundant components we introduce, are equal to 0 if and only if this the y, which is dimension n, is equal to the intended solution x star. So this is an important property that guarantees that our encoding, our embedding of x star to the augmented space is non-ambiguous. We'll be able to chase the solution to this encoded system by pushing this redundant component to 0, and then we will be able to extract the solution we encoded to the solution to the raw system. So now we describe how do we decode. So yeah.
Quick question. So the augmented system is SPSD. Is that assuming that A is?
Yeah, assuming if A is SPD.
Okay, cool.
Right. So now all the discussions based on A is SPD, and we will use conjugate gradient on the encoded system because this is still, although this is a rank deficient, but this encoded system is still consistent, right? So we can still apply CG to it. And now we describe the decoding scheme. So for the purpose of the following presentation, now I partition x tilde into 3 blocks instead of just 2 blocks. So the dimensionality of C plus F is n. So R is dimensionality of K, which is the redundant components. So here we designate some components that corresponding to where the faults happen. For example, the processes that host these components, they fail, and these components will be called faulty components, and their values will not be able to be updated after the faults occurred. So suppose I have this solution, and we can prove that we can decode the intended solution x star from pushing the redundant components to 0. Okay, because we know this is the null space basis, and we specifically want to make this redundant components be 0, then we'll be able to recover the intended raw solution. Okay, so now we look at what do we mean, what property of these 40 components, and how do we deal with it closely. And that's the spirit of this fault oblivious computation. And still we look at this 8x8 matrix, which is augmented by one row and one column, and we try to be fault oblivious to one fault. And then these 9 processes, they participate in the conjugate gradient method, and they exchange the intermediate values of the solution components. For example, P4 and P6 will both store the intermediate values of X5 because they both talk to P5. And each component is updated on the process that hosts it. Okay? So suppose at some point, we will consider P5 is going to crash. But just before it crashes, just before the faults occur, we consider the value of X5 to be given a snapshot value. So this blue X5 means an arbitrary value we don't know, but just a snapshot value just before P5 failed. And we have here we see that both P4 and P6 cache this in snapshot values. That's important. And then suppose now P5 fails, and then we just let the surviving 8 processes, just let them continue their computation, continue the conjugate gradient computation. But now, of course, because P5 fails, these values are no longer available, X5 is no longer updated, and the surviving processes will continue their computation on the subsystem from deleting the 8th row and the 8th column of the augmented system, okay, of the encoding system, right? So they will continue that computation by using the data from the subsystem of deleting the 5th row and column. And here X5 is frozen. The value of X5 on P4 and P6, they still contain the snapshot values, but it's just frozen there. It's no longer updated. And the surviving 8 processes will update other components using the subsystem still available to them. Okay? So the question is, suppose X5 is frozen, the snapshot value is cached on P4 and P6, and until the surviving 8 processes, they are done with their computation on the subsystem. And they have some values for X1 to X4 and X6 to X9. And the question we ask, if I just concatenate those 8 values still updated after the fault happens, plus the snapshot value of X5 before the fault just happened, would that give me a solution to the augmented system? So that's the main question. So if we can solve this question, we'll be able to let the whole computation be fault oblivious, because everybody survives, just continue the computation. Get done with updating the surviving components and use the snapshot values of the 40 components, concatenate with the surviving components, give me a solution to the augmented system. And then I'll be able to decode it, as I already showed how to decode. Okay? So that's good if we can achieve this. So the answer for k equal 1 is sort of trivial, is that if E is a fully dense vector, then we'll be able to do that. So why that is the case? Because if E is a fully dense vector, okay, remember the null space basis is E top on minus ik. That's the null space basis. If E is fully dense, for any 40 components, I can go along that direction because E has a non-zero component in that direction. I can go along as much as we want to, pin down the value of the 40 component at the snapshot value, no matter what it is. Okay, so that's the intuition. So in general, we ask the question, if k is bigger than 1, what is the condition we need to impose on E so that this fault oblivious computation will be correct? So here is the theorem, okay? So let E be the encoding matrix. In fact, we talk about this transpose is a k by n encoding matrix. It consists of k rows but n columns. And we require the critical rank of E transpose to be k. The critical rank of a matrix, of a fat matrix, is the largest k such that any k columns are linearly independent. So intuitively, E transpose is K by N. If we just randomly pick any K columns from that fed matrix, it's non-singular. It's literally independent. Okay, this condition is stronger than E be full rank because it's no guarantee any random K column will be linearly dependent. It just you may find some K columns linearly dependent, but some are not. So closed rank K is stronger than E being full rank K. Okay, so if that is satisfied, then we show that for any value f you give to the 40 components, no matter what value you give it, if the cardinality of this 40 set is bounded by K, then there exists C and R such that the solution to the encoded system is given by CFR. Okay, and the C and R can be computed for the oblivious computation, just running the surviving process until they terminate. Okay, that's our claim. And I skipped the proof here, but just talk about some results of simulation this scheme. So we use 3 matrices, and the first matrix is a synthetic problem, which is a 1D model problem, which is tridiagonal Laplacian matrix. And these 2 matrices are from the UFL sparse matrix computation. And we implement the CG iteration, use MATLAB. And to simulate the faults, okay, we randomly inject K 40 components. We have N components to select from. We just randomly pick K components. Say they are fault. They will never be updated after a certain point of CG iterations. And we determine when we inject these randomly selected K components at random determine a CG iteration. Okay, so we have CG run iterations, and after one iteration of a certain random iteration of CG, we just ping down the values of K randomly selected components, and then we let the rest of the components be updated using the subsystem that has survived. And the encoding matrix we introduce is a random Gaussian matrix, but it's scaled according to the square root of N. So the intuition is that this encoding matrix will have cross-core rank K by high probability. Okay. So here are the results. So this column shows when there is no fault occurs, and this column shows there's one fault occurs, and this column shows there are many faults occurred, 20% of N. So for this matrix, if there is one fault occurs, it's sort of early in the CG iteration. Here is the red cross marking when the fault happens, when the random one fault happens. If that is early in the iterative method, after the faults, the process continues and still achieve the same solve criterion, which is the residual norm less than 10 to negative 10. If we compare the number of iterations, of one fault to no fault, it just a little bit more, it's almost comparable. But however, if we look at this matrix, still there's one fault occurs, but it occurs sort of late in the, if we consider no fault, it will take 300 iterations, and this happens almost at 200 iterations, there is fault introduced. Okay, then it really increases the number of iteration somehow, like almost 300, 200 more than this case. And in both cases, in both of these cases, these 2 matrices, we see that if there are a lot of faults occur, still we can achieve the same stop criterion 10 to negative 10, but it really takes much more iterations. But anyway, it can still do the job, at least. For this matrix, this is a hard matrix because even when there is no fault happens, after 4,000 iterations, which is, the exact number is 10 times the size of this matrix. The size is 416 times 10 is the maximum number of iteration we'll give it. It cannot reach 10 to negative 10. And when there are faults happen, no matter one fault or many faults, it makes the convergence worse compared to there's no fault happens. And I need to emphasize that the plots here show the residual norms That's the residual measured on the augmented system or the subsystem after some faults happen, the surviving subsystem, okay? So that's not the residual on the input raw system. So let's see how, if I get the solution here, I do the decoding back, and I claim that's a solution to the raw system, how that behaves on the raw system. So here it shows the relative residuals on the raw system using the solution we decode from the fault oblivious computation. We can see that for these two cases, when no matter it's one fault or many faults happen, we can achieve very accurate solution, okay, on the raw system. But however, for this system, which is hard, after this many iterations, it can only achieve 10 to the negative 9. When there are faults happen, it can be harm for the accuracy if we use fault oblivious computation. But still, not too bad. We still achieve something, but just not as good as compared to these cases. Okay, so in summary, that we present a way that we can encode the linear system by augment the linear system to introduce data redundancy, and then we can run a fault oblivious conjugate gradient method, which of forgetting those faults, and then you give output something, we can decode back to the solution we want. So there is minimum interference of the computation. We just let it go and modify the conjugate gradient a little bit by introducing faults, and we still do what we want, and there's no other extra overhead. So thank you. So any questions? Yeah.
Can you explain for the last system, the residual?
This curve?
Next.
This slide?
Yeah.
So you want me to answer what are the numbers here?
Yeah, why is the residual compared to the previous two cases?
Why this is worse than this?
Yes.
So the question is why this case is harder than this, right? Yeah. So my understanding is that, okay, first, this linear system is more yield conditioned than these two linear systems, because look at when there is no fault happens, just run on the correct system, there is nothing wrong. After 10 times its size of iteration of CG, it can only achieve, it's stuck there. Okay, it can no longer make more process. And if that is the case, and because when we introduce faults, when faults happen, we're solving a different linear system, which is a survived linear system, which is different from the original one, right? And we get some solution on that subsystem, which still we don't achieve 10 to the negative 10 because this system is ill-conditioned. And then when we decode it back, there are more distortion happens. So in the end, we cannot even match this accuracy. So definitely when the linear system is ill-conditioned and some parts are failed, and it could make the system even more ill-conditioned. And how to understand this and how to precondition the surviving subsystem is open question, is something we can investigate in the future. Yeah.
What is the effect of augmenting your linear system? What is the effect on the condition number? So if you know the condition number of A, then what do you expect? Right,
okay, that's a good question. So yeah, so here, let's go back to this slide. Okay, that's the input raw system, that's our encoded system. And for this linear system, because it's singular, we need to talk about its effective condition number, right? By just restricting to the, by deflating the null space, and because of the interlacing property, we know the n non-zero eigenvalues of this matrix, is interlaced with because it's SPD with this n values, and whether this effective condition number could be better than this, I think it definitely depends on what's the encoding matrix E. It will affect the interlacing property and whether we can bound somehow, So in the experiment, I showed when E is a random Gaussian matrix, which is scaled, and for the random Gaussian matrix, we know it has very good condition that's based according to random matrix theory. We know that eigenvalues are well distributed, and so this E, if we use a random Gaussian matrix, I assume this columns and the rows will be nice, and so the condition number, may not be much worse than this A, but I don't have a quantified answer. But using the knowledge of what is E could help us to understand, how to bound the condition number compared to A, and how do we choose E to, make this even, well conditioned, better conditioned. But I don't have a quantified result at this moment. Yeah.
I think on the previous slide.
This one?
Well, somewhere before that, I thought A tilde was n plus k by n plus k.
Oh, right. Okay, so here, now let me go back to this slide.
Yeah, but based on the one that you were on before for Kyle's question, wouldn't it be n plus n times k?
Sorry,
Am I missing something?
so okay, here. You care about the dimensionality, okay? So okay, A is n by n.
Right.
So E is n by k. E is a tall and skinny matrix.
Right.
So this matrix is n plus k by n plus k.
What am I missing?
So this is the transpose of this one, right? So this is this A times a tall skinny matrix give us a tall skinny column, and then that's the row, and this dimension n by n, this dimension is n by k, n by k, and this is k by n.
Okay.
That's it. Yeah.
Thank you.
Yeah. All right. Yes.
Have you looked at all, so you've shown us plots of the residual after a certain number of iterations. Have you looked at the actual error after a certain number?
I did not measure the error. Because in most of the applications, we don't know the true solution. The solution there are random, just a random solution generated from the interval of 0 to 1. Each component is a random solution, and yeah. So I did not measure the error, but there is work on CG how we can estimate the error, right? But I did not pursue that in this work. Yes.
It's a big question, but the iteration numbers obviously will increase. The number
Right.
of iterations required, but how fast?
So here, to be honest, in our current implementation, when the faults happen, we need to truncate because in CG we need to maintain the search direction, right, P, and when the faults occurs, we just totally delete that search direction, because when faults happens, if we maintain that search direction, and the next step, because you are using the subsystem, there is no guarantee you will maintain orthogonality to the previous search direction. And that's why we totally discard that search direction. Almost, we will restart, and that's why blows up the number of iterations, and somehow, because but still we use the intermediate value of x, right? We'll start from some x value, and we forget about search direction, and then somehow takes many more iterations. So yeah, it's a interesting question of how can we speed up the process, and we can look into flexible conjugate gradient method. Flexible Krylov subspace will give us better understanding of what happens then. Yeah.